Welcome to the online lecture series of heat and mass transfer. Subscribe the channel for the video sessions. Here is Professor Lakshman Mane. This is a video session on heat transfer by transient heat conduction. In this session, you will be able to explain transient heat conduction, lump system analysis and dimensionless numbers. Do you know what is transient heat conduction? Let us see some practical examples. Annealing of steel billets. It is a process whereby a metal is heated to a specific temperature and then allowed to cool slowly in order to soften the metal, which means it can be cut and shaped more easily. Cooling of an automobile engines. Cooling of brake drum of automobile engines. Heat treatment of metals by quenching. It is the process that is the soaking of a metal at a high temperature above the recrystallization phase, followed by a rapid cooling process to obtain certain desirable material properties. And heating of water in solar water heater. In all these examples, the process of heat conduction takes place, that is transient heat conduction. So, in such cases, the temperature may vary with the time. In such cases, the temperature in a body is the function of space coordinates and the time. Means T is equal to function of x, y, z, that is space coordinates, and time t. Solution of such problem is complicated. So we consider those cases where the temperature variation is the function of its position and time. Means temperature is a function of x and t. When the heat is transferred from the body to its surrounding, there will be a variation of temperature of body with time until the body attains an equilibrium state. The period during which the body temperature varies with time to be under unsteady state means transient state. The conduction of heat is unsteady state, which is called as transient heat conduction. Now, how the analysis of transient heat conduction is done? So there is a method called as lump system analysis. Interior temperature of some bodies remain essentially uniform at all times during a heat transfer process. The temperature of such bodies are only a function of time, that is T is equal to function of time. The heat transfer analysis based on this idealization is called as lump system analysis. So consider a body of arbitrary shape where m is a mass, v is a volume, ρ is a density, Ti is initial temperature, A is a surface area, specific heat Cp, thermal conductivity K, conductive heat transfer coefficient H, and temperature of surrounding, that is T infinity. The rate of heat transfer from solid surface to surrounding is given by the equation Q is equal to H into A into temperature difference of T minus T infinity, where H is convective heat transfer coefficient, A is a surface area, and T minus T infinity is temperature difference between the solid surface and the ambient air. Here lump mass, that is m, is equal to ρ into volume, and lump heat capacity is m into c, means ρ into v into c. Now energy balance equation, that is convective heat transfer is equal to decrease in internal energy of body per unit time. Here Q is equal to h into a into t minus t infinity. Putting the value of m here minus rho Cv into dt by dt. Negative sign is for decreasing internal energy of body. So here dt, arranging the last equation, we get dt by t minus t infinity is equal to minus ha divided by rho Cv dt. Now integration of this equation, we get left side natural log of t minus t infinity. This total term is a constant as it is. Integration of dt is t plus c1. This is constant. Now obtain to c1, use initial boundary condition, that is at t is equal to 0, capital T is equal to ti. So ln of ti minus t infinity is equal to, this term becomes 0 plus c1. So c1 is equal to ln of ti minus t infinity. Putting this value in equation 1, we find this term, that is ln t minus t infinity is equal to minus ha upon rho Cv t plus ln ti minus t infinity. Arranging the terms, we find this equation. So here, taking antilog of both sides, we can have left side t minus t infinity divided by ti minus t infinity. And here, antilog of this term, that is e raised to minus ha upon rho Cv into t, is equal to this. We can write in this way. Here LC term comes. This equation gives the variation of temperature of solid on cooling or heating up to surrounding temperature. This LC is called as characteristic length. So here are some dimensionless numbers. This is Biot number is equal to h into LC upon k. Fourier's number, that is alpha t upon L square. Now here ha upon rho Cv t, arranging the equation in this way, then v by a is a characteristic length. Now we can have here some arrangement, that is multiply and divide by k and LC in this case, then separate the term HLC by k and another KT by rho C LC square. After that, here HLC upon k and this term we can write as a alpha upon LC square. So this is thermal diffusivity. Now left bracket is Biot number, right bracket is Fourier number. So thermal diffusivity is alpha, means thermal conductivity upon rho into heat capacity. Thus temperature distribution equation is equal to e raised to product of Biot number and Fourier number with minus sign. Now alpha already we have seen. So thermal diffusivity represents the ratio of internal resistance to heat flow to the heat rate capacity of material. So Fourier number can be written as alpha t upon LC square, putting the value of alpha, that is k upon rho C. Arranging the terms in this way, so we find here rho Vc upon time, and this at the numerator K upon LC, where K upon LC is proportional to the rate of heat conduction and rho Vc upon T is proportional to rate of thermal energy storage in volume. So Fourier number is given as ratio of rate of heat conduction to rate of thermal energy storage in solid. So at the end of this session, you can explain transient heat conduction, lump system analysis and dimensionless numbers. Enjoying the videos of heat and mass transfer, subscribe the channel Thermal Engineering. Thank you.